Alright, this is going to do the odd numbers in class assignment 6.2. The heights of adult females are normally distributed. If you were to construct a histogram of 40 randomly selected women, what shape would the histogram of those heights have? And what pattern would you expect in a normal quantile plot of these data? So, well, if they're normally distributed, then we expect a bell-shaped curve. So the histogram would be approximately bell-shaped. And the normal quantile plot would have data points that would be nonlinear. Actually, the normal quantile plot is very close to a straight line when the data is normally distributed. So we need something that is approximately bell-shaped. Okay, these two answers here. But then we need the normal quantile plot to follow a straight line. So this one. The histogram would be approximately bell-shaped, and the normal quantile plot would have data points that follow a straight line pattern. Right. Problem 3. Scores on a test are normally distributed with a mean of 63.2 and a standard deviation of 11.7. So find the 81st percentile, which separates the bottom 81% from the top 19%. Round to 2 decimals. So visually, we have a normal distribution, and the bottom 81% would be at some x value here. And that means the area under the curve to the left of that score is whatever the percentage is as a decimal. And then this is the top 19%. Notice they add up to 100%. So the top 19% is the area under the curve past that score. And that area is what? You guessed it, 0.19. 0.19. So we can go to our stats calculator, go to normal, and get the mean and the standard deviation, 63.2 and 11.7, and then type in, well, use the the area on the left, so 0.81, and that will get you this number here. But type it in the area box, 0.81, compute. Okay, so 73.47 is the x score. So when x is 73.47, that will partition the distribution into the bottom 81% being to the left of that number and the top 19% being to the right of that number. Assume red blood cell counts. Okay, assume red blood cell counts are normally distributed for women with a mean of 4.577 million cells per microliter and standard deviation of 0.382 million million cells per microliter. Find the value closest to the probability that a randomly selected woman has a red blood cell count above the normal range of 4.2 to 5.4 million cells per microliter. Okay, so this is kind of throwing us here. They tell us the normal range, but we need to find the probability that a randomly selected woman has a red blood cell count above the range. So we have to take the rightmost value of the range and then find the area under the curve to the right of that number. So we would have, say the range is something like that, 4.2 to, let's see, what was it, 5.4. So this is the normal range. But it's this range that the problem is asking for. So find the probability that the blood cell count is above 5.4. The red area is that probability. So the red area is the probability of a blood count higher than the normal range. Okay, so we need to get our, we were given a mean and a standard deviation, so we type them in. And we don't have to use the million, since they're both 1 million. This is 4.577 million. This is 0.382 million. We can leave the million off. So 4.577 and 0.382.382. So 5.4. Compute. Well, this is the probability of having a blood cell count less than 5.4, but we want the probability of having a blood cell count greater than 5.4, so we need this area here. Well, it's the complement of the area we have here, so we can use the between function or subtract this area from 1. So that's the complement. 1 minus 0.9843. .0157, so it would be this value here, 0.0156 if we had included more decimals. Computers are commonly used to randomly generate digits of telephone numbers to be called. When conducting a survey, can a non-standard normal distribution be used to find the probability when one digit is randomly generated it is less than 3? Why or why not? What is the probability of getting a digit less than 3? Well, a non-standard normal distribution cannot be used because randomly generated digits have a equal chance, so that means a normal distribution, or uniform, excuse me. Meaning that each number is likely, just equally likely to be chosen. And the probability of digit less than 3. Well, we have 10 digits total. 0, 1, 2, 3, up to 9. And the digits less than 3 are 0, 1, and 2. So the size of that set divided by the size of the sample space, 3 over 10, or 0.3. Find the indicated IQ score. The graph to the right depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. So let's go to our normal calculator. We know the mean is 100 and the standard deviation is 15. So what x value corresponds to? Well, that's an area to the right of the x value. If we take the complement, that would be 1 minus the area to the right, 1 minus 0.2525. We'll get the area on the left here, but it'll be the same score that corresponds to this area as the score that corresponds to this area here. So 109.99, rounding that to 110. Okay, assume that adults have IQ scores normally distributed with a mean of 97, standard deviation of 19.9. Find the first quartile, Q1. That is the score separating the bottom 25% from the top 75%. Okay, so graphically, the first quartile would be something like this. So quartile means 25%, right? So the area of first quartile is 0.25. Go to your calculator, type in 0.25, and the mean is 97, the standard deviation 19.9, then compute. So adults with IQs of 83.57 or less constitute the 25th percentile. So the first, which is the first quartile. So the first quartile is 83, the upper bound for the first quartile, 83.6. Use the accompanying data set on the pulse rates and beats per minute of males to complete parts A and B. Find the mean and standard deviation of the pulse rates. So clicking on this icon, we get the pulse rates, and we can open that in StatCrunch. We are asked to find the mean. So recall stats, summary stats, columns, variable 1, mean, and it does say find the standard deviation, so we might as well select mean and standard deviation while we're here. Compute. And it gives us 71.87 and 12.21. So the mean of the pulse rates is 71.87. It says round to one decimal place, so 71.9. Standard deviation, one decimal place, so it looks like 12.2. explain why the pulse rates have a distribution that is roughly normal. Okay, did we have a hint here? Well, there's a hint. Some of these problems are saying, well, this one says because the histogram is bell-shaped and symmetric. Well, we can go and make a histogram, right? If we do histogram, graph, histogram, select our column, compute. And to me, that looks, yeah, roughly bell-shaped and roughly symmetric, about 70, 71, yeah. So the pulse rates have a distribution that is normal because a histogram of the data set is bell-shaped and symmetric. So treating the the unrounded values of the mean and standard deviation as parameters, and assuming that male pulse rates are normally distributed, find the pulse rates separating the lowest 2.5% and the pulse rate separating the highest 2.5%. Okay, so we want to know what pulse rate goes here. The lowest 2.5% would be an area lowest 2.5% corresponds to area equal to 0. Turn the percent into a decimal, 0.025. Right, and then we'll use the mean and the standard deviation that we got from StatCrunch. So what was that? 71.87 and 12.21. I'll use. Or since it says unrounded, we could just take these and copy them into, just stay on the same StatCrunch. Go to Stat, Calculators, Normal. And then we can just highlight the mean, Control C to copy it. Can highlight the mean here on the normal calculator, Control V to paste it. Oh, it looks like I didn't copy it somehow. There it goes. And the standard deviation, highlight, Control copy, highlight, Control V, and that's good. So we need the X corresponding to an area of 0.025 to get the bottom 2.5%. Compute 47.94. So that's the X value that bounds off the probability corresponding to the lowest 2.5%. So 47.94. Come here, round to one decimal, so 47.9. And the pulse rate separating the highest 2.5%. So the highest 2.5% would be the right-sided tail. So somewhere around here. So that's area corresponding to the highest 2.5%, which means that all of this area over here is 1 minus the percentage as a decimal. So since our calculator is based on areas to the left of the score, we can plug in that number 0.975 using the same mean and standard deviation, and we'll get the x bound for that cutoff. So 95.79, we'll round that to 95.8. So pulses 95.8 and above are in the highest 2.5%. And that concludes this the odd